then I'll open Blackboard. PowerPoint, sorry. I'm saying all my different packages here wrong. Well, for some reason, okay, here we go. All right, any questions, issues, concerns, problems? All right, if not, we're in Chapter 11, Vectors and the Geometry of Space, in Section 11.2, Space Coordinates and Vectors in Space. And this is on page 764. We're on this blocks rectangle, you might say, in the middle of the page, just about. These are, I don't know, properties of vectors in space, characteristics, something like that. Okay, so in space you gotta have 3 dimensions. On a plane, 2 dimensions. Space, 3 dimensions. Okay, now, so in space, vector U's gotta have 3 components. We usually think of these as X, Y, and Z components, but you don't have to name them that way any way you want to. 1, 2, 3 components is how they're doing. The components in component form would be U1, U2, U3. V is also a vector in space, so it has those 3 components, V1, V2, and V3. So these are both vectors in space. C is a scalar. Okay, the following are, like I said, characteristics, definitions, descriptions of how we can talk about vectors. First, what do we mean by the fact if we say, well, vector U is equal to vector V? What would that mean? Okay, that doesn't mean they have the same length. They do, but that's not enough. Okay, what it means is that's true if and only if the first component of U is exactly the same as the first component of V. Second component of U is exactly the same as second component of V. Third component of U is precisely exactly the same as the third component of V. They must be identically the same. Now, they could be the same number written in different forms, like one could be 3 halves and the other could be 6/4. Hey, that's the same number, okay? So, or 1 1/2 or something like that, as long as they have the same value. They are equal to each other, okay? So that's what it means to be equality of vectors. So a vector 2, 3, 4 is not equal to a vector 3, 4, 2, okay? Can't do it, okay? They have to be component by component precisely the same, okay? Second, in component form, if V is represented by a directed line segment from some point P, now this is a point, those are vector components. These are point coordinates, okay? This would be P1, P2, and P3, okay, in parentheses. That's point P1, point P. Point Q is a line segment going from P to Q. Q would be Q1. The coordinates of Q would be Q1, Q2, and Q3. Then the vector V, which is V1, V2, and V3 from 4, is precisely Q1 minus P1, comma, Q2 minus PQ2, comma, Q3 minus P3. Okay? That's how you do anywhere in space where you have the 2 points, then the component would be initial or final minus initial for every one of the components in the right order. Okay, so that's how we define, if we have 2 points in space, the vector between them in the direction from P to Q would be that. Number 3, the length of a vector. Okay, given by these double bars here on either side, vector in the middle, that's also called the magnitude of the vector. Okay, and that would be the square root, and when you say the square root, you're implying the positive principal square root of V1 squared plus V2 squared plus V3 squared. Okay, that's it. Okay, the square root of that. These obviously, whether V1 is positive or negative, V2 positive or negative, V3 positive or negative, guess what? When you square them, they're not going to be negative anymore, okay? So you have all positive numbers under here, or zeros perhaps, and take the positive or principal square root. The length of a vector is always, always, always a non-negative quantity. It could be 0 if that's a 0 vector, but otherwise it's a positive number. Length or magnitude is always positive. Okay? Next, a unit vector in the direction of v. Okay? Well, it's the vector v that gives it its direction divided by the magnitude of v that normalizes the length to be a 1. Okay? Now, other way you could write this is 1 over the magnitude. This is going to be a fractional form, a positive fractional form, times the components v1, v2, and v3. Now, of course, for this to make sense, v cannot be the 0 vector. Any other vector in the world, yes, but not the 0 vector, because the 0 vector has a magnitude of 0, and you can never divide by 0. And it doesn't make any sense anyway, okay? Because what is the direction of the 0 vector? It has no direction. It's not even there, okay? But we have to define it there, okay? Then, vector addition, pretty straightforward. By components. Everything, just about, if you do them by components, that's the way to go. So vector addition, if you're adding vector v to vector u, that's v1 plus u1, comma v2 plus u2, comma v3 plus u3, okay? That's how you add vectors. Scalar multiplication, just think of that scalar as being outside. Okay, here comes Houston. We're more than halfway here. Houston is here. Okay, so that gets us 5 out of 8. Hopefully the others will be showing up too. So think of scalar multiplication as c times the vector v. So put c in front of v here, put c in front of your angle bracket here, and then think of this as distributing. C times v1, comma c times v2, comma c times v3. That's exactly what you get here. That's scalar multiplication of a vector. Those are the principles, I guess you would say, characteristics, properties of vectors, okay, in space. And if you go back and check, very, very similar to what we had in a plane, okay? Note that they call them properties of vector operations listed here. Though that was back when we were talking about vectors in a plane, they are also true here. So let's move to, if it'll move to, example 3. Now you can also find this one at larsoncalculus.com for an interactive version of this type of example. Find the component form, that's the way to go folks, and the magnitude of the vector having initial point, vector v, having initial point -2, 3, 1, terminal point 0, -4, 4. Okay? Let me get my writing pad here. I almost feel like I'm back in the pioneer days when you wrote on a slate. That's what I feel like I'm doing here. So let's first do the component form of the vector v. What would vector v be? Angle bracket. What's first? Component by component. You always do terminal minus initial. So the first one I'll write out in gory detail, 0 minus a -2, comma, -4 minus a 3, comma, 4 minus 1. That's it. That's all you have to do. Well, let's carry it forward. 0 minus a -2 That's a positive 2, comma, negative 4 minus 3, negative 7, comma, 4 minus 1, 3. There it is. There is the component form of the vector v, having that initial point, that terminal point. Now find the magnitude of that vector. So what's the magnitude of vector v? Now I can't write bold, so I put the arrow over it. That would simply be the square root of 2 squared plus minus 7 squared plus 3 squared, which would be, gory detail here, 4 plus minus squared is plus 49 plus 9, which would be the square root of 9 plus 49 would be 58, and 2 would be, and 4 would be 62. Now, is there any perfect square we can pull out of that? 4, no, nothing else. So the square root of 62 is fine. Now, we've done the first two here, component form and magnitude. Really helpful to do the component form first before you attempt the magnitude, because then it's such a piece of cake to do. Now find the unit vector in the direction of v. Well, they didn't say to rename it, so I'm going to name it u, and I'm going to put the caret on top, if I could get the pen to write. That's how I represent a unit vector for my purposes. And this is in the direction of v, so I'm going to put v down here as a subscript so I know what unit vector I'm talking about. In that direction, and that would be the vector v, which is 2, negative 7, 3, divided by its magnitude, the square root of 62. Okay, and frankly, that's a perfectly good way to write it. If you wanted to write it a different way, it would be 2 over root 62, comma, negative 7 over root 62, comma, 3 over root 62. Now, if that is indeed a unit vector, what should be true about it? Magnitude 1. Well, it should work out that way, because if you were to square each of these and add them together and then take a square root, if I could get my pen to show up somewhere here. There it is. Okay. Square this, you get 4 over 62, and this would give you 49 over 62. 4 and 49 would be 53 over 62. Square this, you get 9 over 62. So what does I say? 53 plus 9, sure enough, is 62 over 62 is 1. Yep. If you did it right the first time, you got it the second time. All right, and that's indeed what they got. And that's sort of how they wrote it too. They actually wrote the first one as 1 over root 62 times the vector. It doesn't matter. That would be a perfectly good answer. This would be a perfectly good answer, or the way they did it, 1 over root 62 times 2, comma, negative 7, comma, 3. That would be a perfectly correct answer. Any one of those three would be fine. This is what they wrote finally. That's what I wrote finally, but they started with this one. I started with that one. Either one, fine. Okay. Any questions? Example 3. Okay, what I'm going to do, if there are no questions, is erase my scratch, and let's see how they did it. Component form, just like we said, they spelled it out for you. Q1 minus P1, comma, Q2 minus PQ, comma, Q3 minus P3, where Q is the terminal, P is the initial, and just like we got 0 minus a minus 2, negative 4 minus 3, and 4 minus 1, which gave you 2, negative 7, 3, just like we got. Okay? That implies the magnitude, or the length, or whatever you want to call it, to be, the magnitude of that is the square root of the first one squared plus the second one squared plus the third one squared, which is root 62, which is what we got also. Then to find the unit vector in that direction, and they use this term, the vector u2. Now understand this. I just want to go back a few slides. Notice there's vector u. That doesn't imply by any stretch of the imagination that's a unit vector. Just because it says u, okay, doesn't mean that. Here, that does. They're using u because it is. And that, in my mind, is one reason to, rather than just bold, and you can't tell if that's a bold unit vector or just a bold vector, because all of vectors are bold. That's why I like to have the arrow over it if it's a general old vector, and put the housetop, the whatever they call that symbol, over the unit vector. So that's why I do the unit vector. It helps me to distinguish any old u from a unit vector u. And this is the unit vector u because you're taking v and dividing it by its magnitude. That's the definition, which is 1 over 62, which they didn't quite do. They pulled the 1 over root 62 out and then wrote the vector v here, and then writing them component by component, basically distributing that constant inside the vector. Excuse me. I must have swallowed something wrong. Okay. Okay, I must have gone too far. Let me also say this, because I don't think it'll influence this class any or make a difference, but just to let you know, I think all of you know I have a mild form of leukemia, and it's nothing really that I ever sweat about. I discovered I had it back in 1991. Now, I'm not going to ask how many of you were alive in 1991 or what age you were in 1991, but that's how long I've had it. Almost 30 years now, 29 years. I doubt if any of you are 29 years old. Okay, so it's nothing that I'm really, it's just I've lived with it that long. But it took 17 years before the counts got high enough they even wanted to do a treatment on it. And that's because back in those days, the treatment was worse than the disease. It was a really rough treatment. They did a bone marrow transplant, which was, my hematologist said, if you can avoid that, hang in there, we'll get better treatments coming up. And sure enough, they did. So my first treatment was in 2008, and it was a fairly, not super harsh, but it was chemicals, 2 chemicals. Didn't make me, well, I think it made my beard turn white, but it didn't make me lose any hair. This was just natural. But it did, it did occasionally make me nauseous, when I was doing the treatments. I had 4 rounds of it. Drove the counts way down, but didn't wipe out the disease. So ever since then, I've been doing other treatments, not as harsh as those were. They're called the monoclonal antibodies, which, by the way, same type of thing that the president got for COVID. For those are experimental, which means they could have some side effects they don't know about yet. But I guess since he's president, he can have whatever he wants, okay? But these are tested, and these have basically been developed since I've gotten the disease. So that first doctor was very wise, saying, hang on, things will get better, and they have been. So they're treating the disease. But, and I don't know if Kyle maybe will remember this, maybe Houston too, from last spring, I had a treatment at the very 1st of January, the day before we came back. The faculty had to be back on campus. and it was a drug I had used before, and it's been very effective every time I've used it. But this time it was really effective. It drove the counts way, 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 way down. But at the same time, it drove my red blood cells down. It drove my platelets down. It drove everything down. Not as severely as it did the whites. That's what it was targeting, but it drove everything down. So the doctor got sort of upset, not upset, but concerned that possibly it was causing some damage to other things, and he did a bunch of blood work on me after that when he saw the anemia and stuff come in, and basically everything was sort of okay. There was nothing to be super concerned with. So went on and had the next appointment. That was in the spring when counts were really low. Then early summer, when I had the next appointment, the white cell counts, they climbed, not dramatically, but it climbed. They were outside the range, but back then COVID was really pretty scary for everybody. So he said, better not to have a treatment. And I was all in favor of that too, because of the last treatment, how it knocked everything a winding. I wanted to get more white counts out there for it to attack and not have it attack as many red blood cells and platelets and other things. Well, had the blood work done last Friday, and in having that done, found out the white cell counts have really gone up. I knew they would because they were already up before, but red blood cells, platelets, everything else has taken a nosedive too without a treatment. So now he's concerned with what's going on here. So he had me go back in this morning before I tried to be there soon after 7 as I could when the lab opened, and they did blood work again. You can see my patch there. And so they're trying to make sure that the disease cells are the ones that are going to be affected the most by the chemical, by the monoclonal antibody. In other words, they're doing the markers on the cells to make sure the ones that this monoclonal antibody attacks, that marker is strong, so it'll have a good target to go for. And also checking to make sure that no anemia is happening. I have anemia, but that it's not caused by either. Well, he's trying to determine what's causing it. Because last time it was okay until after the treatment. This time it was okay in June, but then went really south here. So that's not, it's a little bit different. So anyway, the whole purpose of saying that is when I get really tired, that's probably because I'm very anemic now. So that's my excuse. Now I have an excuse for being tired. I thought it was just being 69, but I guess I have a more excuse now. So that's why when I stop and have to get something to drink or something like that, I'm just trying to boost a little bit of energy. So sorry for all that, but I wanted to let you know. So I will be having a treatment probably next Thursday and Friday, because it's been more than 9 months since my last one. They want to start me back over and do a 10% the first day and 90% the second day. So that won't affect this class any, but it will affect my Tuesday, Thursday classes. So Thursday classes are probably gone. Some of them will lose. Hopefully I'll be back in time to do the afternoon class if they can schedule me in the morning. Okay, so then Friday of next week, we don't know this yet. That hasn't been scheduled yet, but more than likely it will be then. I will not have office hours that day because I will be at the clinic. Okay, and that also will probably affect my office hours on Thursday. Now let me time out here. I think I said this on Monday, but let me tell you again now. Because I'm on second mini-term now, my physical science class is different from the one I had first mini-term as far as the hours go. So that has opened up for me to have office hours from 1 to 3 on Tuesday and Thursday. I did not have those times free on first mini-term, but I do have them now. I haven't gotten those changed on every place they show up in Blackboard. I got them changed in the instructional materials. I put my new locator card for the second mini-term out there. So you'll see it there, but in the other places I forgot they had me put my office hours about 3 different places, and I forgot to go back and change the other 2 or however many there I have. So I'll try to get that done sometime this week on top of everything else. So it's been a crazy week, and it will continue to be so. So trying to get things normalized. All right, any questions, especially on example 3? Okay, sorry that took way too long of an explanation. Okay. Now, recall from the definition of scalar multiplication that a positive scalar positive scalar multiples of a non-zero vector v have the same direction as v. They're just either longer if that positive scalar is greater than 1, or shorter if the positive scalar is less than 1. But it's always in the same direction as v. Whereas the negative multiples have the direction opposite of v. Same orientation, same the parallel, but in the opposite direction. And then the scalar quantity, if it's absolute value of that scalar is less than 1, that's a shorter vector. Greater than 1 is a longer vector, but in the opposite direction. The negative sign changes direction, but the absolute value gives how much it's scaled. In general, 2 non-zero vectors, u and v, and I don't think this u is unit vector, no longer that, u and v are then parallel when there is some scalar c such that u is equal to c times v, or v is equal to c times u. You could say it either way, and that c could be positive or negative. It could be a fraction or a decimal. It could be a whole number, a mixed number, rational, irrational. It doesn't matter. Any real number c. If the absolute value of c is less than 1, you've scaled it down. If it's greater than 1, you've scaled it up. If it's a positive c, you're in the same direction of v. Negative c, u is in the opposite direction of v. So here's the definition of parallel vectors. 2 non-zero vectors, u and v, are parallel when there is some scalar c, any real number in the world other than 0, okay? 0 would still, well, no, it wouldn't work. Some scalar c not equal to 0 such that u is equal to c times v. Because we already said they're non-zero vectors, so if the scalar was c, even though vector v was not 0, if the scalar c was 0, then that would make u 0, and we can't have that being. So they should say some scalar non-zero scalar c. Okay. So for example, here in this figure, we see vectors u here, vector v there, and vector w here. Okay. They are all parallel. This vector v is in what we call standard position, meaning its initial point is the origin, pointing up here. Okay. Now, by all appearances here, u looks like it's about twice v, and that's what they say it is. So its scalar is 2. That could have been 1.9 or 2.1. We can't distinguish that, but those would also have been parallel vectors. Okay. But w does appear to be only in the opposite direction, so its scalar is -1. That changes the direction because it's a negative, but it doesn't change the magnitude because the absolute value of 1 is 1. Okay, so that's what we mean by scalar multiplication, basically. That produces a parallel vector in the same direction if the scalar is positive, opposite direction if the scalar is negative, and the scale, absolute value of that scalar, determines whether it's a stretch or shrink or whatever. So here's example 4, middle of page 765. Vector w has initial point 2, -1, 3 points there because of the parentheses you see here. Terminal point -4, 7, 5. Which of the following vectors is parallel to W? Well, I think probably the first thing to do is figure out what is vector W. And if we do this, I think we'll have a really good idea if either of these is parallel to it. Okay? So, what would be the components of W? This is terminal point, there's initial point. Anybody? Earth to class, come in please. -6 for the first component, second component. Anybody? 8, -1 minus, I'm sorry, 7 minus a minus 1, it would be 7 plus 1 is 8. First component was -4 minus 2, that's a -6. Third component, terminal minus initial, 5 minus 3 is 2. Now, we look at these. Ha! That is indeed W is equal to -2 times V. Agreed? -6 times -2, 3 times a -2 is -6. -4 times a -2 is +8. -1 times a -2 is +2. This one, oh, look at that. Nope, not quite. The numbers are such, but the signs are not. Notice these signs, plus, minus, minus, this is minus, plus, plus. That fits. But minus, plus, plus won't fit with a plus, minus, plus. Okay? No way you can make that happen. Okay? Because if you multiply by a positive number here, multiply this by, or is it that this by a positive number, then these numbers, that order would stay minus, plus, plus. That's not what we got here. Multiply by a negative number, it would be a plus, minus, minus. That's not a plus, minus, minus. Even though the scales are, this 12 is twice 6, the absolute value of that. 16, the absolute value of this is twice 8, and 4 is twice 2, but you have to have the same sign by all three of them, corresponding signs. You don't have that. So the answer is U. You are the answer. Okay, never mind. I thought you were the problem. No, never mind. Okay, so begin by writing W in component form, which is precisely what we did, and they got precisely the same result. They did write theirs out. I was too lazy to do that. I just pointed out what it was, and we got those. Then you compare. Because they did it the other way, U is exactly -1/2 of V. Oh, they didn't name, no, W. Then you can conclude that U is parallel to W. But on the B part, you want to find a scalar that makes that true. For the first one, a -2 would work. For the second one, the -2 works. But the third one, -2 would not work. If that had been a -4 there, yes, that would have been also parallel. But +4, not. Okay. Any questions? Does that make sense? Okay. So to find C, equate the corresponding components. So that's sort of what I said. The first one and the second one, C equal -2, worked. It looked so promising until you got to the third one, and that C was a +2. Not going to happen. Not going to happen. They all would have to be precisely the same number with precisely the same sign. The third one does not have that. All right. Any questions? All right. That means that the equation 12 -16 4 equal C times -6 8 2, no solution. The vectors are not parallel. I wouldn't have even written it that way because you tested it, it didn't work. That makes it you think it did. It doesn't. Oh my goodness, that's the last one on the slide set. But they do have a number 5 still in the book, so let's see if we can do number 5. I think we'll need to go to the whiteboard. So determine whether these points, oops, first time here, and the whiteboard's all screwed up. Well, not screwed up, just, you can't see this, but I have a taskbar here that's in the white space. Why do they put it in the white space where I can't write? I don't know. And then, because y'all are over here on this side, you don't see that either. I want to move my whiteboard as far to the left as I can. Okay, and here comes Jesus Miguel. Okay, so let me admit him to the class and mark him on the roll. Okay, we got 6 out of 8. Jesus or Miguel is here. All right. Now, I'm playing with my whiteboard now, trying to get it where I want it to be. Okay. Now, Miguel or Jesus, we're on Chapter 11, Vectors in the Geometry of Space, 11.2, Space Coordinates and Vectors in Space, and we are doing example 5 at the bottom of page 765. Okay, just getting ready to write it down. Okay, so here's 3 points. Point P has coordinates 1, comma, -2, comma, 3. That's a point. Those are parentheses. Point Q has coordinates of 2, comma, 1, comma, 0. Parentheses. Okay. Point R has components 4, 7, -6. Okay. Determine whether those points are collinear. What in the world do we mean by that? That means they all lie in the same line. Okay. Now, let's consider what the implications of that are. If they're collinear, okay, take any 2 of them and determine the vector representing those 2. Okay? Take one of those and the third one and see what the vector there is. Now, from those 2 vectors, you can tell whether they're parallel or not. Okay. And if they are parallel and one point is in common, because you chose 2 and then one of the other 2, one of those with the third one, that has a point in common. If they're parallel with a point in common, they got to be collinear. You can have a parallel vector here with here, and they're not collinear. But if they share a point anywhere on that a point, and they got the same direction, they are collinear. So that's what we've got to do, is determine 2 of the vectors. So the first one, let's do PQ. The vector PQ would be what? You tell me. Earth to class, come in please. 2 minus 1 is 1, comma. 1 minus a minus 2, that's 1 plus 2, 3, comma. 0 minus 3 is a minus 3. Okay. Now, we see what vector that is. Let's do these 2. It doesn't matter, any 2, but let's do QR. as in a QR code. Okay. That would be 4 minus 2, 2. Okay, don't throw out the baby yet. 7 minus 1 is 6, comma, 6, or negative 6 minus 0 is negative 6. Okay, the question you ask yourself, are these two vectors parallel? Sure enough, vector QR is exactly twice PQ. 2 times 1 is 2, 2 times 3 is 6, and 2 times negative 3 is negative 6. So since they have point Q in common and are in the same direction, you know they are collinear. They are collinear if I spelled it right. All right. Okay. And they chose different points for the second time. They did the same point for the first one, then they did PR for the second one. They've got the same result. Okay? Any questions on number 5? Let's go to example 6, top of page 766. I'm going to clear the drawings. If no one has any question, we'll clear that if I can hit the right key. And let's do this. Standard unit vector notation. Write the vector V, where is my pen? There it is. Write the vector V, which is equal to 4i minus 5k. 4i, and I do the caret because it's a unit vector. 4i minus 5k, also assumed to be a unit vector. Okay? So write that vector in component form. Is this based on the last problem? They didn't have that. Oh, no, I see. Okay, sorry. Write that vector in component form. So V, I consider that component form. That's how I had it growing up. Now I see what they're saying. Write it in an angle bracket component form. What would go here? 4, comma, help me somebody. Just because you have I and K without a J, that implies you're in 3 space, because you don't have a K in 2 space. So that would mean the J is 0, and then this is negative 5. So that's the vector V in component form. That's the A part. The B part. Find the terminal point of the vector. Here's the vector V, different vector V here, by the way, which is 7i unit vector minus j unit vector plus 3k unit vector. Okay? Given that the initial point P is negative 2, comma, 3, comma, 5. That's a point. And here I'm running out of juice. I'm sorry. Hold on. I don't know if this really helps, but it's a great placebo. Hopefully that can boost me a little bit. Now I have an excuse. I'm anemic. I thought I was just old and tired before. Okay. Now, if that's your initial point, what's your terminal point? Well, what do we know? We know that 7 is equal to, can I use the term Q1 minus a minus 2? Remember, that's how we got this. If we'd have known the terminal point, Q, which would have been Q1, comma, Q2, comma, Q3, that's what we're looking for. This is what we're looking for, so let's plug in what we know. Well, that means add a negative 2 to both sides, so your Q1 would be, add a negative 2, that would be a 5. We also knew that negative 1 would equal Q2 minus 3, minus the initial point. Add 3 to both sides, Q2 is equal to Q2. Okay? And we would know that 3, the component here, would be Q3 minus 5. Add 5 to both sides and you get 8 is equal to Q3. So the terminal point Q would have to be 5, 2, 8. Does it seem right for that to be true? Did I do a dumb mistake here? Nope, 5, 2, 8. That's exactly it. Now I think I've just run over my cord with my chair, or no, I got it stuck on something. I don't want to damage this. My wife paid too much money for it. Okay, but I married money, so that's fine. Okay. Now, I don't think I have room for C on this slide, and since it's a brand new problem, let's go on and clear this. Anyone need those two left? Do you see what I was doing? Using the same, I'm sorry, losing my voice too. Using the same values we did before of getting your component form by subtracting here, we did the same thing here, but now we knew the component form. We didn't know the terminal point, but we knew the other two, so do your equations. That's what we did. All right, let's go to C. Find the magnitude of the vector V. So this is what we're looking for, magnitude of V, when V is equal to -6 I plus 2j minus 3k. Then find the unit vector in the direction of V. I thought they would ask that. So first, what's the magnitude of V? How do you get it? The principal square root of the sum of the squares of the components. -6 squared plus 2 squared plus a -3 squared. Actually, you could have dropped the minus signs all along, but just wanted to keep them there. It's the square root of 36 plus 4 plus 9. Oh, that kind of works out nicely, doesn't it? The square root of 36 and 4 is 40, plus 9 is 49. Principal square root of 49 is 7. So the magnitude of V is 7. And the second part says find the unit vector in the direction of V. So I use my notation for that. The unit vector U, I put the hat on it to let you know that, in the direction of V. I put it as a subscript. That's not standard. That's just my way of telling that's the unit vector I'm talking about. Okay, so what would this be? It would be the vector V divided by its magnitude. So if it's okay, I'm just going to write it down. I'd prefer to write it down in component notation, but since they gave this one in IJK notation, I will write this one down too. That would be negative 6 over 7 I plus 2 over 7 J minus 3 over 7 3/7 K. Now, how do I check and make sure that is indeed a unit vector? I take the square root of the sum of the squares of those components. So minus 6/7 squared would be 36/49 plus 4/49, that's 40/49 plus 9/49 is 49/49, which is 1. So sure enough, that should be true. And let's see what they got. They put the ones, oh no, here they did. Negative 6/7 I plus 2/7 J minus 3/7 K. Good for them. I'm proud of them. All right. Any questions on that one? All right. If no questions, I'm going to go on and clear it. And let's take a look at number 7. Okay, now this requires a little bit of physics, and I can't recall that all of you have taken physics. I know most of you have, but perhaps some of you haven't. A television camera weighs 120 pounds. It's supported by a tripod, shown in this figure. And since you can't see my book, I'm going to show it to you just briefly, if I can hold it up that long. Okay, where is it? There's the camera and the tripod. Okay, the feet of the tripod appears to be, I can't pick out the numbers, is Q1, Q2, and Q3. I think Q1 is that the one at 0, -1, 0, and Q2 is at square root of 2 over 2, 1/2, 0, and Q3 is at minus square root of 2 over 2, 1/2, 0. I'm reading backwards, very small print. Let me see if I read them right. Q1 was 0, -1. I hope I said that right, 0. Q2 was minus root 3 over 2, 1/2, 0, and Q2, oh, I'm sorry, I had those two backwards. Q2 was root 3 over 2, 1/2, 0, and Q3 was minus root 3 over 2, 1/2, 0. And the camera itself is up there at 0, 0, 4. Okay. Now, here's the only part of this that really does require physics. And I think common sense will tell you that too. The weight of the camera is pointing straight downward, and its magnitude has to be 120 pounds. So it's in the minus Z direction at 120 pounds. Okay? Now, so represent the force exerted on each leg of the tripod as a vector. Okay? Now, this is going to be sort of nasty. I'm going to not draw the camera. You'll be thankful. So that's going to be on the Z-axis. So I'm going to put the Z-axis here. I'm going to put the Y-axis over here. I don't draw the isometric very well, so I'm going to do it like this. And mine doesn't going to look very good. This is your X, there's your Y, and there's your Z. Okay, I'll tick off a few. I need probably a negative back here and a negative over here too. You don't need a negative down because nothing's going below the plane. Okay? Now, Q1 was at 0. Okay, let me tick off some points here. Let me widen them out here. This be sort of like they are in the book. There's going to be a -1. There's going to be a +1. Here's going to be a +1. 1. And here's going to be a +1. And we'll make this a +1, +2, +3, +4. Okay. This is where the camera is. Its weight is pointing straight down the z-axis, and that's 120 pounds. So the scale is for displacement purposes, not for weight. Okay, but the magnitude of that weight downward, I want to call that W for weight. Its magnitude is its vector quantity, because weight is a vector quantity, 0, 0, -120. Sorry, the pen is writing really strangely. Okay, all the weight is pointed toward the center of the earth. Okay, now represent the force exerted on each leg of the tripod as a vector. Okay, oh, and I was starting to write the legs of the tripod. This one's at 0, -1, 0. This one over here is at, and that I think they called Q1, I believe it was. Q2 over here is √3/2, 1/2, 0. So the 1/2 is going to be here, √3/2. That's about 0.8 or something like that, 0.866, something like that. So it's going to be something about here. Drives me nuts. Okay, there we got that point. And then this one's at negative 1/2. Let me make sure I did that right. Negative √3/2, 1/2, 0. So negative √3/2, that would be about 0.8 again, somewhere right in there. This is just, okay. Somewhere here. Okay. Now, my picture doesn't look very good, I guarantee you. But that's supposed to be the tripod. Okay. Whew, this is a long problem. So, we want these three forces, this to be F1. This, I think, was F2. This is Q2. Okay. Okay, yeah, that's the point. So that's going to be √3. This drives me nuts. √3 over 2, comma, 1/2, comma, I'm leaving out one. Oh, 0, yeah, okay. 0 in the z direction. Okay, and this point over here is negative √3 over 2, 1/2 in the y direction, and 0 in the z direction. Okay. All right. Now, if you look at this little triangle made here, and this is going to be hard to see because my origin is almost in line here, that triangle there, the sides of that triangle are 4 this way, I don't want to do this in a terribly complicated way. All right. This vector F1 right here, we know, okay, let's get this right. We know it's the vector here, F1. Now this isn't the magnitude of the force, I don't think. It's just the vector in the direction of F1. Okay? And I just don't like the way they're writing this. They need a scalar next to it. Okay? And by the way, one thing they said, I guess, or I guess you have to assume it. Oh yeah, no. What you have to assume here are all 3 of these legs are the same length. Okay? They didn't say that in giving the problem, but they're assuming that in the course. And when you have a tripod, usually that's what that means. Okay? Now, to name this F1, meaning a force, then it would need a component of this 120 in it. It doesn't have that. Okay, this is just a direction. This is just a displacement here. Okay, not really a force, and that's why I hate they call it the force 1. It's in the direction of this for sure, but it's not the vector. Okay, so I'm just going to call this V1 if it's okay. Vector V1, which is force F1 is in that same direction. This would be, this is the terminal point, there's the initial point, so that would be 0 minus 0 is 0, negative 1 minus 0 is negative 1, and 0 minus 4 is minus 4. Okay, so that's the vector here. This vector over here, which I'm going to call V2, I hope I don't get into trouble doing this. Okay, that's a vector also. That would be root 3 over 2, comma, 1/2, comma, negative 4. Because this minus that. Okay. This one over here, I'm going to call V3 is equal to negative root 3 over 2, 1/2, negative 4. Can't read my writing here. There's negative 4. That's vector. I've got, no, there's the vector part. This was a, there's the vector. Okay. All right. I'm going to have to get me something else. My throat is going on me fast. Let's see. Okay. I prefer calling those vectors, not the forces, because the forces, the magnitude of the force well, we'll get to that. Okay, but these are the vectors in those directions. Okay, now because all three legs have the same length and the total force is distributed equally among the three legs, you know that the magnitude of each of those three have to be equal. Now they're calling them the forces now. Okay, and if the magnitudes are all equal, there is some constant C such that okay, now I get what they're saying now. They're using sloppy notation. They were talking about the directions of F1 and F2 and F3, and they said F1, F2, F3. They were meaning directions. So they use the vector PQ1, PQ2, and PQ3, okay, with P being up here at the top, and this is Q1, Q2, and Q3. So what I'm calling V1 is vector PQ1, and that's in the direction of force 1. This vector here is PQ2 in that direction, and this one here, I'm going to write it out here, is PQ3, okay, in that direction. Okay, now what they say next is this one. Now this makes sense. F1 vector F1 is some multiple C1 of this one, 0, 1, or that's -1, -4. Vector C2, F2, sorry, is that same magnitude, that same scalar quantity, times that vector here, which is √3/2, comma 1/2, comma -4, and force vector 3 is also that same thing times -√3/2, 1/2, -4. Oh man, I don't know. I'm losing it quickly here, folks. Before I felt I was just tired. Now I think I know why I'm tired. Okay, now the total force, like I said here, is this one. They're calling this, if I can find my pen, come on pen, oh there you are, and now it's decided not to be a pen anymore. Okay, this is going to be, this is what they call the total force F, and the F is equal to the sum of those three. Okay, now so if you added those together, C would be common on all of them. So then, and what are we supposed to find? The force exerted on each leg as a vector. Okay, so we're wanting to know what F1 is. Okay, so basically what I would do then is, if you write this way, F, which we know, is 0, 0, -120. And that's equal to the C times this plus C times that plus C times that. Okay. Now, first thing that I think I would do is factor out the C and divide it here. Okay, divide both sides and make this negative 120 over C. I think that would be easiest. And then, if that is indeed true, you have minus, this is driving me nuts. Okay, minus 4, let's just do the third component because these add to 0. Minus 4, minus 4, minus 4 is equal to minus 120 over C. Or we could have left the C's in here. Okay, and then this would be minus 12 is equal to negative 120 over C. So that appears that C is equal to 10. Okay, well then all you have to do is multiply 10 times each of these, and that would be 0 minus 10 minus 40. This would be, yuck, 5 root 3 5 minus 40. Yeah. And this one would be, let me clean this up a little bit here. It's really crowded in here. I can't erase too much. I did erase too much. Okay. This would be minus 5 root 3 comma 5 comma minus 4, I think. No, minus 40. It should be an angle bracket. Goodness gracious, I'm losing it fast. So 0 minus 10 minus 40, 5 root 3, 5, negative 40, and negative 5 root 3, 5, negative 40. Yes. Sort of a convoluted kind of problem there. I didn't like their notation there, and that was throwing me off, but they said in the wording in the direction of this, but when they wrote it, they didn't write it. That indicated that. Any questions on 11.2? Okay. Homework exercises here would include, now always look at the concept checks. Make sure you can think through what they're asking you to think through there and do. Always a good idea to do that first. Then the homework exercises would be any of the either 5 or 7, both at Calc Chat, 9 or 11, both at Calc Chat, but 9's at Calc View. Any of the odds 13 to 23, they're all at Calc Chat. 25 or 27, both at Calc Chat, 25's at Calc View. 29 or 31, both at Calc Chat. 33 or 35, both at Calc Chat, 33's at Calc View. Any of the odds 37 to 41, all at Calc Chat, 39's at Calc View. 43 or 45, both at Calc Chat. 47s should be at, I'm losing it again, should be at Calc Chat. 49 should be at Calc Chat. 51 or 53 should be at Calc Chat, with 51 at Calc View. 55's at Calc Chat. 57's at Calc Chat. 59 or 61 are at Calc Chat. 63 and 65 are at Calc Chat, should be. 63 should be at Calc View. 67 and 69 at Calc Chat. 67 at Calc View. 71 should be at Calc Chat. Any of the odds 73 to 77 should be at Calc Chat. 79 and 81 are at Calc Chat. 79's at Calc View. 83 or 85 should be at Calc Chat. 87 should be at Calc Chat. 89 should be at Calc Chat. 91 and or 93 should be at Calc Chat. Any of the odds 95 through 103, they should all be at Calc Chat. All right, goodness gracious, let's see if I can make it. Part of it is probably hunger too. I only had time for a salad in between my first two classes. I'm going to go down and get a sandwich. I got it made, but I didn't have a time to eat it. So let's go back to, now we're going to move to 11.3. Any questions on 11.2? Okay, let me get rid of 11.2 here. Goodness, that was loud. Okay. And I thought I got rid of it, but I didn't. So let me close this out here. And now, let me do 11.3. I hope this is 11.3. Yes, it is. Okay, 11.3, still Chapter 11, Vectors and Geometry of Space. 11.3 is the dot product of two vectors. Now again, for those who have had physics are probably, this is old hat to you. For those who haven't had physics, you may have run into this before. Like, I can't remember, did we do this in trigonometry? Anyone recall? Math 113? You don't recall it? Okay.
Yes.
And we did do dot products there?
Yes.
Okay, good. I thought we had. So this, again, will be sort of a review, and even some of the applications will be sort of review-ish, but some of them are new too. So the dot product of two vectors, here are our objectives. Got quite a few on this one. Use the properties of the dot product of two vectors. Find the angle between two vectors using a dot product. Find the direction cosine of a vector in space, cosines. Find the projection of a vector onto another vector, and use vectors to find the work done by a constant force. Okay. So let's start with the dot product. You have studied two operations with vectors: vector addition, which you can say addition or subtraction, and scalar multiplication, multiplication by a scalar, each which yields another vector. In this section, we'll study a third vector operation, the dot product, but this dot product yields a scalar rather than a vector. Okay, rather bizarre, multiplying two vectors together and getting a scalar answer. Okay, and that's called a dot product. So the dot product, now here's one definition, and it's certainly true. This is the easiest one to use. Okay, definition of dot product. Let's say you have, and now they're going to 2 space, here they go to 3 space. This isn't a plane. U is U1, U2, V is V1, V2. Component notation. The dot product of those two vectors would be U1 times V1 plus U2 times V2. That's it, folks. You multiply the corresponding components together and add them to the product of the other corresponding components. If you're in 3 space, you do it 3 times. U1 times V1 plus U2 plus times V2 plus U3 times V3. That's your dot product. A scalar answer. Okay? Multiplying two vectors, getting a scalar result. Okay? Now, here in theorem 11.4 are your properties of these dot products. Okay? Now, remember, U, V, and W are all vectors in the plane or in space, either one. C is a scalar. But if you're in plane or in space, all three of them are in the same one. Okay. Now here's one property. U dot V, same as V dot U. And you see that from this definition. It doesn't matter which one you multiply first, V1, U1, that's the same, because multiplication of the numbers, and that's what the components are, just numbers, is commutative. So it doesn't matter which order you do. Same thing here. That's the same as V2 times U2. So therefore it doesn't matter which order you dot. Okay? So dot product is commutative. Okay? Now here's a slightly different one. The vector U dotted with the sum of V plus W, okay, that's the same as U dotted with V plus U dotted with W. That's a distributive property of dot products, okay? The dot product over the sum of two vectors, okay? Now here's another sort of an associative property. C times the dot product of U and V, now this is going to be a scalar. That's going to be C times U dotted with V, which would be a scalar. Or you could distribute it's not really a distributing, multiply the C times the V. Only one or the other. Either multiply it by U and dot it with V, or multiply it by V and dot that with U. Either one of those will give you, and they're calling that an associative property, but it's an associative property of a scalar multiplication with a dot product multiplication. Now here's another one, that old pesky zero vector, which doesn't really act like a vector at all. The zero vector dotted with any vector in the world. Any vector, no matter how large or whatever, is always going to give you the numerical answer 0, because the dot product of two vectors is a scalar. And that makes sense if you go back here and say if one of these was a zero vector, let's say U was, that would be 0, 0. Or down here, 0, 0, 0. Dot that with V, be 0 times V1 is 0, 0 times V2 is 0, 0 times V3 is 0. That would give you the scalar number 0. 0 plus 0 plus 0 is 0. Now, here's one you may find is slightly unexpected. A vector dotted with itself is basically its magnitude squared. Okay? Well, let's go back here and see if that makes sense. If this was V and that's also V, that would be V1, V1 plus V2, V2. Okay? And, sorry, or in 3 space down here. Okay? Well, that would be V1 squared plus V2 squared, right? Or V1 squared plus V2 squared plus V3 squared. Well, guess what? That's the square of the magnitude. And that's what this is saying. It's the square of the magnitude of V. Perfect. All right. Example 1. Yeah, we have time. Let's do that. If I can find my pen. All right. Let U be 2, negative 2. V be 5, 8. W be negative 4, 3. So let's take the dot product of U and V. Okay? Anyone do that for me? Product is 2 times 5, 10, plus negative 2 times 8, a negative 16, and that gives you negative 6. Right? Let's see what they got. Whoa, I didn't know they'd be underneath me. Oh wait, I went to the wrong place. Let me erase my scratch here. And they get 2 times 5 plus that, and you get negative 6. Perfect. Okay, let's do the B one. This is u dot v, which we just did here, -6, times w. I wish they hadn't done the work for you. This would be, now notice that's a scalar multiplied by a vector. That scalar multiplication, you're still going to get a vector. That would be positive 24, -6 times -4, comma, -18. Okay, I think that'll be in the way again. Yes, it will. 24, -18. Good deal. Okay, let's do C. I wish hadn't done the first part for you. U dotted with 2v is the same as 2 times u dot v. Well, u dot v we found out was -6, so that's 2 times the -6, and that's -12. Okay, gonna be a scalar because dot products are scalars. This was going to be a vector because that is a scalar times a vector is a vector. Okay, and I bet you that's going right on top of it. It is. So let me clear this. Oh man, I'm out of energy. And the phone's ringing downstairs, so I can't mess with it. And that's -12, just like we got. Okay, let's see if there's a D. Yeah, there's a D. What is W, the magnitude of W squared? Well, that's just the dot product. You don't have to do square roots anymore. It's the dot product of these two. That is that squared. Well, that's 43.43. We can do that. -4 times -4 is 16 plus 9 equal 25. And now we also know what the length of W is. It's going to be 5 because it's the square root of that. Okay, the magnitude is going to be 5. All right. Well, let me erase mine. Okay. 25. Perfect. Is there an E? No. Notice that the result of part B is a vector quantity, whereas the results of the other three parts are scalar quantities, because magnitude is a scalar. When you square it, it's still a scalar. Dot product is a scalar. Dot product is a scalar. Okay. Now, how are we doing? 4 more minutes. Let's see what we can do in 4 minutes. Now we're going to talk about the angle between two vectors. Now, we gave you, and we've done, the easy definition of a dot product. But guess what? It has at least one more and possibly 2 more really good definitions too. And that's what we're going to do here. The angle between two non-zero vectors, now of course the angle between them implies they're not the same vector too, is the angle between two non-zero vectors is the angle theta, and it's going to be between 0 and pi. So if it's between 0 and pi halves, it's an acute angle. If it's between pi halves and pi, it's an obtuse angle. So it's either going to be an acute or an obtuse angle, and this is between their respective standard position vectors. Okay, the angle between two non-zero vectors, the angle between theta between 0 and pi between their respective standard position vectors is shown here. The next theorem shows how to find that angle using a dot product. So what we're looking for is this angle here, given these two vectors here. Now they look close to 90 degrees, but they're not. Okay, so don't be fooled by that. Okay, now I'm sorry, just so little time to go and I just can't. they throw in this up here, that this is equal to V minus U. There is V, and add to that the opposite of U, which would have been something in this direction here, and we would have had a vector here which would have been exactly parallel, same length as that one. Okay, so there they've drawn that little triangle for you. Now what's that angle in between there? Here's the theorem. The angle between two vectors, if theta is an angle between two non-zero vectors u and v, where theta is between 0 and pi, then here is the answer. That's equal to the dot product of the two vectors divided by the product of their magnitudes. Okay, they're just giving it to you. That's what that angle is. Now it says, note that the theorem 11, that because magnitude of u and magnitude of v are always positive, remember a magnitude is always positive, u dot v and the cosine of theta will always have the same sign. So if u dot v is negative, that means cosine theta is negative. That means theta is between minus, well wait, we don't use negative angles, so that would mean, well, we'll get to that later. Okay, but they always have the same sign. Okay. Now, I think that just ran us out of time. All right, where are we going to pick up next time? We're on this right at the bottom of the page. Okay, bottom of page 771. Okay, homework exercises here, not too many, but let's see what we got. I think you can do any of the odds 3 through 9 and stop there. Even though we talked about what this angle is, we'll wait until we do the examples first. So in section 11.3, 3 through 9, they're all at Calc Chat. 3 is also at Calc View. Any questions? Okay. If not, if you don't have any questions, we will call it quits for today. I've still got one more class and 3 of you will be there, I hope. So I hope I'll make it to. I think once I eat the rest of my lunch, I'll feel a little bit better. So I'm going to stop sharing for now, unless there's some question on what we got on the board, or I can go backwards. And well, where did it go? Where did it go? There we go. Let me scoot this over some so I can get rid of this. Okay. And unless you have some questions, I'll end the meeting for all of us. So any questions? 2, 4, 6. 6 out of 8 were here today. Glad y'all could make it. So unless, okay, some of you are leaving already. We'll see 3 of you in just about half an hour, and the others I will see next week. Have a good weekend. Bye.